Hey everybody, how's it going? So welcome back to chapter 13. Today we're going to walk through an example of how to calculate a dependent samples t-test or a paired samples t-test or a related samples t-test. Those are all the same thing. So what I've got for you here is some data, and we've got 12 different participants. And let's say that what we're doing is we're going to have all these participants take a quiz, a math quiz. And then we're going to have them listen to Mozart music, and then we'll have them take kind of a similar quiz and see if listening to music actually improved their quiz scores. All right. So we've got their quiz scores for quiz number one and quiz number two. Remember, these are the same people giving us two different scores on the same variable, which is how well they did on the quiz, right? Now, ultimately, what we need to get to is over here on the right, this calculation t equals d bar, that's the mean of the different scores, minus zero. That's actually the hypothetical, the null hypothesis population mean difference score would be zero. That means, hey, if these two quiz scores really aren't different from each other at all, meaning the Mozart music didn't do anything, you wouldn't actually expect to see any difference between them. And so that's why the difference scores, the average difference scores, would be expected to be zero. So it's kind of nice because we actually kind of don't worry about that part of the equation at all since it doesn't do anything. The denominator is the standard deviation of the difference scores, and we divide that by the square root of n. So that gives us, again, estimated standard error on the denominator term. So let's walk through how you would go about doing this. The first thing that we're going to do is we're going to have to calculate the difference scores, right? So you could put in difference up here, make that a little bigger. Now, typically speaking, it's common practice well, you need to think about which one of these are we subtracting from which one, meaning quiz one from quiz two or quiz two from quiz one. If the hypothesis is that Mozart music actually increases the quiz scores on average, you probably want to take the post-test scores, meaning quiz two, or post manipulation scores rather, quiz two minus quiz one, because that means that the outcome, if in fact the Mozart music improves quiz grades, you'd expect a positive difference because the scores after will be higher than the scores before. So what we're going to do is we're going to take, I'm going to hit equals. I'm going to click on this first participant's quiz two score, which is an 8, and I'm going to subtract their quiz one score. Okay. I'm going to hit enter, and that gives us a difference of positive 1. That makes sense. 8 minus 7 should give us 1. Now, the cool thing is all you have to do is you click on that cell for the first difference score we just calculated, and in the bottom right-hand corner of that cell, you can see that there's a kind of a very small green square. I'm going to click on that green square and I'm going to drag this down for all of my participants, and then Excel just automatically calculates the differences between quiz two and quiz one. And you want to just double check, right? So, okay, so for participant two, 9 minus 6 should give us 3. Yep. For participant three, 7 minus 8 should give us negative 1. Okay, cool. So now we've got our difference scores, but we don't actually have anything here yet. We don't have all the stuff we need. We need to calculate an average difference score, a mean difference score, which is called D bar. So I'm going to put mean and in parentheses D bar, if that helps you. And what you do there is you hit equals, and the function for calculating a mean or an average is called average. So I just start typing in the word average. You should actually see something pop up that says function average. I'm going to double click on that, and it says, hey, which numbers do you want me to average together? We just click and drag, get all of the numbers. I hit enter, boom. That is our mean difference score, 1.58. All right. So we've got one piece of the puzzle over here. We've got basically our numerator taken care of. Now we need to figure out the standard deviation of the difference scores. And we do know how many people are in our sample. Well, there's 12 people in our sample. 12 people in our sample. Okay. So we need to find the standard deviation. Very good. I'm just going to put down like st.dev there is the way that I remember standard deviation. You could also put capital S, capital D, or what, whatever you could write out standard deviation, whatever helps you. And so to do that, you type in equals, and the function actually is stdev dot s because this is a sample. If it was a population, we'd use stdev dot p, but we're using a sample, so I want stdev dot s. So I double click that, and it says, hey, which numbers am I trying to calculate a standard deviation for? And I'm going to click and drag all of those cells, all those values, hit enter, and there we go. We've got our mean and we've got our standard deviation, our mean of difference scores, D bar, and our standard deviation of difference scores, S sub D. Excellent. So we're pretty much there. We just need to plug in the numbers and calculate this t statistic. So I guess we could take it piece by piece. Let's try to calculate kind of the bottom piece first. What we might do is, and you can do this wherever you want, but I'm just going to put it like maybe I'll put it over here. Well, what's the square root of n? Okay. What's the square root of n? Well, to do that, there's a function. You type in equals and start typing in SQ, and it is SQRT, is square root, SQRT. And it'll say, which number am I trying to take the square root of? And I'm going to put in 12 because we have 12 participants. Our sample size n is 12. Hit enter. That's the square root of 12. Okay, cool. Now I want to figure out if we're going to get our denominator here, which is the standard error, I'm going to type in standard error here, and we'll bring that out a little bit. Okay, we're going to actually take the standard error, which is this whole term on the bottom, is the standard deviation. So I'm going to type in equals and click on the standard deviation of difference scores that we just found, divided by the square root of n. Well, we just found what that is right here. So I'm going to just divide those things to get the standard error. Cool. That's our denominator. Okay. And so now all we have to do is put it together. We've got D bar, and if we divide that by our standard error, we get the t value. Okay, so I'm going to put in t right here equals D bar divided by standard error. Hit enter, 3.8. Nice. So this is our observed t-score, right? Do we know if that's significant or not? We do not know if that's significant or not. We're going to have to look up in a t-table, depending on whether we have a one-tailed test or a two-tailed test. Also, going off of degrees of freedom, and degrees of freedom for a paired samples t-test is n minus 1. So that would be a degrees of freedom of 11, right? 12 minus 1 is 11 degrees of freedom. We'd look that up, and let's say it's a one-tailed test because I think that Mozart music is going to help increase people's scores on the second quiz. We look up a one-tailed test with a alpha level of 0.05 and a degrees of freedom of 11. We'd figure out what the critical t-score is, and we would compare our observed t-score that we just calculated, 3.8, against whatever that critical t-score is that we look up in the table. And then we can say, hey, if it's in the critical region, we get to reject the null hypothesis and conclude that this is a significant t-score. And what that means is that there is a significant difference in quiz 2 grades compared to quiz one grades for these participants. Okay. All right. Hopefully that was interesting. Thanks a bunch, and I'll see you in the next one.